Hi, I'm Lauren Bearden, and today I'm going to be talking about coastal processes. So basically, coastal processes are things like wind and current and waves that help shape and sculpt coastlines. And coastlines can vary vastly based on where they're located. So coastlines in the southern parts of the United States, like Florida, tend to look really sandy and beachy, whereas coastlines in the northern parts of the United States usually are rocky and there are cliffs. And then coastlines that face the sea a lot of times have coral reefs. There are three principal processes that influence coastlines, and they are erosion, transportation, and deposition. Erosion is basically just the breaking down of land by the force of waves hitting the shore over and over and over again. Transportation is when waves and tides work together to transfer material like sediment elsewhere. And then deposition is the process where waves lose energy, they stop transporting, they let go of their eroded material, and thus this helps shape the coastline. There are four ways that waves specifically erode the coasts. Hydraulic action, which is when air gets trapped in the cracks of a cliff and it compresses and it weakens the cliff over time. Abrasion is when pieces of rock and sand hit the cliff over and over and over again and grind the surface down, kind of like the way sandpaper would. And then attribution is when waves break rocks and they become really small and smooth. And then solution is when certain types of rocks are dissolved by seawater. So these have just been a few examples of what coastal processes are and how they shape coastlines. So I hope you enjoyed learning something new today, and thank you for listening.
So one topic in understanding coastlines is the shaping of shorelines. The interaction of plate tectonic processes and geological structures with waves, longshore currents, tidal currents, and storm surges help shape shorelines in different forms. One of the most popular examples of a shoreline is a beach. A beach can change over a period of time from as little as a day all the way up to a year. A beach can be made up of many components from sand, rocky headlands, dunes, bluffs or cliffs, and a tide terrace. So some of the main parts of a beach are you have low tide levels, high tide levels. This part would be your backshore, your foreshore. You have your surf zone and your swash zone. The balance of adding and removing sand from a beach is from the inputs and outputs caused by the sedimentation, transport, and erosion. An example of an input would be sediments eroding from the backshore cliffs by waves. An example of an output is sediments being transported to backshore dunes by winds. Three important causes of a shoreline are plate tectonics, erosion, and sedimentation. Erosions happen when waves hit rocky shorelines, causing the rocks to fall. And lastly, shorelines such as sandbars, low-lying sandy islands, and extensive tidal flats form where sediments tend to build up depressions in Earth's crust.
So for my section of coastlines, I will be talking about continental margin. What makes a continental margin? So for me personally, I like to think of it as the beach. You're moving from the land to the ocean. So here is a diagram of a continental margin. Some key terms here is the continental shelf. This is the most economically valuable part of the ocean. A lot of fishing and oil drilling actually happens here, especially in Louisiana and Texas. The continental shelf fluctuates with the rise and low of sea levels. Also, during the Pleistocene ice ages, all the continental shelves that we have now that are 100 meters or lower were above sea level during that time. And glaciers would form on top of these, and as the glaciers would travel and move or melt, this caused these shelves to have very irregular shapes. In the continental shelf, the active sediment transport is what moves sediments right here to the edge of the continental slope and rise. The slope and rise is below the sea level quite drastically, so it's not affected by waves or currents. So what moves these sediments is the turbidity currents, which is a very thick, muddy water down the slope. These are much more dense than the ocean, which is what allows them to kind of roll along the bottom. these erode and transport sediments down the thick, muddy continental slope. As they come out towards the end, they can actually form a submarine fan, which is a lot similar to the alluvial fans that we talked about in our labs on the topography maps. These also can form submarine landslides, which is when the slumped over material at the top of the shelf can kind of bunch up a bunch and just flow down drastically. These can sometimes be caused by earthquakes, or it can cause randomly. Sometimes they can even be formed by methane water, which is when the ice that is formed by methane and water melts due to the pressure of the sea level dropping. It can cause it to form a landslide. Also, turbidity currents can form submarine canyons, which are deep valleys eroded into the continental shelf and slope, which is this diagram here. So within the continental margins, there is active and passive. Active margins are caused by volcanoes and earthquakes. This is also caused for two plates that have subduction. So as one plate pushes under another, they can form a wedge, which is material that has bunched up from the scraping. They can also form the borearc basins, which is when magma melts material and pushes it up to the top. Both of these are labeled at the bottom of the diagrams. A passive margin is called passive because it is not geologically active. There are no active volcanoes, and most earthquakes that occur here are very random and sporadic. They're not very active, or you can't have them in a sequence. And that is labeled here at the top.
Hi, my name is Sarah Reeves, and I'm going to be talking about the topography of the deep sea floor. The definition of topography is the arrangement of natural and artificial physical features of an area. Some terms you need to think about when you're looking at the deep sea floor are mid-ocean ridges, volcanic hotspots, which you can think of Hawaii, deep sea trenches and island arcs, which you can think of the Marianas Trench, and continental margins. Here we have a topography map of the Earth laid out. Here we can see a few ridges, like the Pacific Antarctic Ridge, the Mid-Atlantic Ridge, and we can also see a few trenches, the Central American Trench, and I mentioned the Marianas Trench earlier, and the Southwest Indian Ridge. Here we have a picture of a cartoon picture of the Mid-Atlantic Ridge. Right here, it shows how new crust is formed after volcanic activity. The crust is formed from lava cooling by the water. Here we have a few pictures of how the topography of the ocean floor is mapped. Some of these machines are manned. They go down to the ocean floor and look at them. Others are remote controlled from a boat above the water. And then others can use sonar, which is just beams being shot down from a boat all the way to the ocean floor. Here we have another topography map. This one is of the Atlantic Ocean. This is what the ocean floor would look like if we were to drain all the water. You could start at point A and work your way all the way to point B, and you would see a slope, a rise. It would plane out. You could see a valley, and then it would slope back up again once you reach Spain. And here is another version of that map for the Pacific Ocean. Right here, you start at point B and work your way to point A. You can see the Australian continental shelf, the Tonga Trench, which I want to note that is the deepest trench in the world. You see volcanic islands. You'll make it all the way to the East Pacific Rise, and then you'll come to the Peru-Chile Trench. And that's it. Thank you.
Hello, my name is Lauren Northington, and this video is for geology, pick your poison coastlines. My topic is ocean sediment. I'll go ahead and say excuse my appearance and sound at this time. My allergies have led to a sinus infection. So why is ocean sediment important? And what does it include? So there are technically 4 types of ocean sediment. There's terragenous, biogenous, hydrogenous, and cosmogenous. Terragenous is transported to oceans by river and wind from land sources, i.e. erosion from land that eventually ends up into the ocean. A lot of the times this is stored in submarine canyons until it can make its way to the ocean floor. It's usually carried to the deep sea by turbidity currents, and then turns into turbidites, which is the thick, layer of sediment, which ranges in size from, very small microscopic to larger. Most of it is types of clays, quartz, and volcanic ash, things from land. There's also biogenous. It's the second most abundant type of sediment. That's usually the remains of the hard parts of ocean critters, shell fragments, coral reefs, diatoms, radiolarians, siliceous sponges, and silicoflagellates. Also, the hydrogenous is the third. That's directly precipitated from water, chemical reactions in the water. Rock evaporites, formed by the evaporation of the salt-bearing water, things left behind on the rock, when the water evaporates. Most of it's calcite, sometimes aragonite, and then some of it's metal sulfides from the hydrothermal vents in the deep ocean. The fourth type is cosmogenous. It's the rarest, and it comes from extraterrestrial sources. Microscopic spherules, which are, and also large meteor debris. Collisions of meteorites with Earth. So that one's really there's not a lot of that. It's important to study the seafloor sediment because you can study past climate change. You can study offshore pollution patterns, find sources of dredged material for beach replenishment, locate offshore minerals, and it just kind of helps you figure out what is getting dumped into the ocean because it all ends up in the bottom anyway. So I hope this was a little bit informative, and have a great day.